Okay, so 5A, Lab 10, y'all open to the correct page?
Yes, page 40.
Okay, so we're looking at chemical reactions today. So, chemical reactions and how we keep track of what's happening during a chemical reaction. You know, we've talked a little bit about physical change. Remember when we made the ice cream, that was a physical change from a liquid to a solid. But that's just physical. But chemical change, we're going to see some things take place. So what makes a chemical reaction different than a phase change of matter, than a physical change? We're going to see that today. We're going to see where there's actual exchange of information between two molecules. Okay, the molecules are going to trade out stuff. Someone's going to give something, somebody's going to take something, that kind of thing. So what happens in a chemical reaction? I will tell you, there are a few clues to tell us a chemical reaction has taken place. And we did one of those. Remember we saw, didn't we do the little iodine clock where we watched it and it was clear and it turned dark all of a sudden? We did that in this class, right? Yeah. So we saw a color change, right? We saw it from clear to that dark color. So that showed that a chemical reaction took place. We've also, have we used Jiffy Juice in here? No. Okay, because it changes color, but it's not a chemical change. It's a physical change because it's just indicating. It's called an indicator. We'll work a little bit with an indicator today, and it just shows something that is happening, but it is a chemical thing that's happening. It's just the indicator makes it more visible. Okay, it indicates that it happened. All right, so back to our periodic chart of the elements. Okay, this is important. I'm going to put this where y'all can hopefully see them from some vantage point on your tables. I don't have one for everyone. Okay, you get mine from college here. Okay, so just have it where you can visualize what's going on there. Remember, we put this together as a puzzle, and we can see that the shape was shaped in such a way that it's very specific to what's going on. So we all understand what an element is. Yes? What does the atomic number on the chart tell you?
How many protons?
How many protons it has. And for the sake of on the chart, when we're just looking at it, it also tells us how many electrons there are, right? But remember, electrons are what do chemistry. So those are the things that are going to be moving and changing. That's what makes chemistry happen, is the exchange or sharing of those electrons in the outer shell. Okay? That's what chemistry is. All right, so we know what elements are. Do we know what molecules are? What's a molecule? What's a molecule?
Like a certain molecule, let's say, an example molecule is the oxygen molecule.
Yeah,
Or the
an
water
O2.
molecule.
Water molecule, H2O, right? It's usually one or more, two atoms.
It's like two atoms of different substances?
It doesn't have to be different, so you could say an oxygen molecule is O2. It's both oxygens, right? Yeah, N2, that's a nitrogen molecule. An atom is a single by itself, and a molecule is multiple ones, whether it's H2O, H2SO4, C6H12O6, whatever it is, those are molecules, or atoms that are put together, all right? And furthermore, we're going to see that the way that they're arranged in these columns, it's going to be very important to us today about where they are on the periodic chart of the elements. That's why I have it in front of you so you can see it, all right? Because the way it's arranged is giving us very valuable information about the kind of chemistry that will take place in all these guys, okay? Now, one thing we also already know, all the guys all the way on the right side, remember those guys all the way over there? Helium, neon, argon, krypton, those guys in the far right column? You see them?
Mm-hmm.
Look on the far right column. What do we know about them?
They have a stable electron configuration?
Absolutely. They're full in their outer shell of electrons, right? How much chemistry do they do?
No.
None. Unless we really, really work on them and make them do it. Okay, so we can manipulate them, put a bunch of energy in there and that kind of stuff and make them do it. But they are naturally not going to go do any chemistry. They don't need anything. They stand alone, right? They're inert. Inert means inactive. All right, so unless we really, really mess with them. So they're in group over here, number 8. All right, can anybody remember what a molecule is? You remember what an atom is? I'm sorry, an element is. An atom would be, of course, what the element's made of, right? What are the 3 main parts of the atom? 3 main parts of an atom.
Electrons, protons, and neutrons.
Electrons, protons, and neutrons, right? And the neutrons are the ones you have to figure by looking at the atomic weight versus the atomic number. The atomic number will always, always, always represent the protons. Always, right? Every time. That's what makes it what it is, however many protons it has. Okay, so can you remember now what an ion is? What's an ion?
It's like a molecule with a charge that's either negative or positive.
Yeah. Typically, when we talk about an ion, we're looking at an atom,
Yeah, no.
so an individual. But today we're looking at molecules as well. Okay? It's because there are molecules that take on a charge. Okay. So I'm backing up just a little bit so we can remember this. So the difference between an atom and an ion are that the atom is neutral. All right? Because it has the same number of protons as electrons. They cancel each other out. They're neutral. I've got two here in this particular case. I have 2 protons. I have 2 electrons. I have no charge on that molecule, on that atom. Okay. We always remember that the number of protons is what defines it. So if we're looking at here at something with 2 protons, what are we looking at? Chart will help you. 2 protons.
Hydrogen?
2 protons. Helium. It's helium. Yeah. Now an ion has either given away an electron or stolen an electron. All right, so in this particular case, which this doesn't really happen with helium, but let's just pretend like it does. We have 2 protons and only 1 electron. That means there's 1 more positive charge than there are negative charges, giving this thing right here an overall positive charge, right? It's an ion. So ions are electrically charged because their protons and electrons do not match up. Now, here's our neutral atom. If we lose an electron, we're losing a negative charge. Okay? It's kind of weird to think you're positive because you've lost something, right? But if we lose an electron, we have more positive charges here. So this thing is called a cation. We have to remember this. Let's remember it this way. Cat, look at that big plus sign right in the middle of it. Cation. And then anion would be the -1. It has gained an electron. It has gained a negative charge. And it's called an anion. So just be very positive, even if you don't like cats. Pretend like you do. Cats make you feel positive. Cation. Plus. Okay? All right, you need to know that for this next thing. Now, looking at your chart, we have the chart arranged in such a way because they tend to act similarly in the families on the columns. Okay, so the column's going down. This column, column number 1, column number 2, skip all these weirdos in the middle, column number 3, 4, 5, 6, 7, and 8. Okay? The weirdos in the middle just have strange behaviors. You have to do extra chemistry to get to know those guys better. This one shows it. But look at this number at the top. What this number is telling me is that over here, let's not worry about hydrogen so much. Well, we could. Hydrogen has 1 proton and 1 little electron sitting out there. It would like to have another one, to have 2, and then it would be full and it would look just like helium. Remember, the goal of every one of these guys on your periodic chart of the elements is to look like that guy in the last column. Just with the electrons, not inside because they can't change their protons. But they can put on a coat of electrons, right? And they can appear to look like neon. They can appear to look like krypton from the outside. That's the goal of every atom on the thing. They're all trying to achieve greatness with the 8. I'm saying great with 8 in there. Greatness. Okay? All right. So if we look at everything in row 1, in column 1, what we know about is every single one of these. Their outer row of their valence electrons equals 1. They each have 1 valence electron, and boy howdy, they'd like to not have that one just sticking out there by itself. They either want to gain 7 more, yikes, that'd be hard to do, or just lose the 1. And then their shell that's left behind looks just like the previous noble gas. All right? So they are eager to give away an electron. Does that make sense to you? Is everybody catching on here?
Yeah.
Okay, they're eager to give away. Like, do you have a question, Josh?
Oh, no,
Okay.
I was looking at this and I think Albert Einstein had an element named after him.
Absolutely. Some famous people do. I think Madame Curie, Curium is on there.
Lawrence.
Laurentium. I'm not sure what Lawrence is, but Mendelevium after Mendeleev.
There's
Yeah.
There's American.
Somebody from America got it named that.
California.
I've got ink everywhere. Okay, so now that we know this, check it out. This next group, they have a 2 above here. I put a +2 right there. These guys have 2 electrons spinning around in their outer shell that they would just like to get rid of. They give them away. They'll share them, whatever it takes, so that they don't have those two just hanging off the end there. So they have what we call here this valence number called +2. They want to take on a +2 charge by giving away 2 negative charges. Yes? Make sense? Okay. Next over here, these get a little wonky. Notice they don't go all the way down. But essentially, group 3 is going to be +3. Group 4, they don't even show them on here, are going to be plus or minus 4. The most famous in that group being carbon. Plus or minus 4. And that's kind of hard to do, right? Because if I'm trying to get four things, there's 8 total that I'm looking for, and 4 is half of those things. Yikes, that's a lot of work to do. So those particular ones, carbon in particular, will end up sharing 4 electrons. It'll make a deal. It'll cut a deal with somebody else on the periodic chart of the elements, namely hydrogen. Hydrogen has got 1. It says, I'll come in, I'll share that with you. All right, and then our next group, so this is 1, 2, 3, 4, 5, 6, 7, and 8. So look at group 7. Group 7 has 7 valence electrons. How many does it want? 8. So what does it need? It just needs 1 more electron, and it will be happy. It'll be fulfilled. Its goal in life will have been achieved. Yeah? Okay, so that's all it needs. So notice it says it's -1. It would like to take one negative charge to itself and become a negatively charged ion. You get it? Yes.
I think like it's confusing. Like the natural thing you would think for this charge is if it says +1, it wants 1 more. And you say
Right.
-1, it
That's
wants
what gets
2 more.
confusing about the idea that an electron is a negatively charged thing. So when you're gaining a negatively charged thing, you're getting a negative charge. It is confusing. Just keep in mind that the electron is negatively charged. Okay, so here's how we're looking at it. So this group +1, this group +2, +3. This is plus or minus 4 depending, but +4 is the most famous being carbon. -3, -2, -1, and of course our group over there that does nothing, right? Our noble guys over there just sitting pretty on their thrones. Okay, now you're going to have to sort of remember these numbers for our next bit of information, okay? All right, this is now getting to notes. If the formula that you're working on is ionic, in other words, it forms ions. Did we talk about what makes something ionic? You have 1 metal and 1 non-metal. Did we talk about that?
I don't remember. It was on the test though.
Yeah, I should have put another slide in here that talked about an ionic compound is one that has a metal and a non-metal, and they give and take electrons between them. I'll show you an example here in just a minute.
I thought it was just getting one from.
No, it has to do with metal, non-metal. Okay, and you know the metals and the non-metals. There's the jagged line going on our periodic chart of the elements. Everything to the left is a metal. Everything to the right is a non-metal. Okay, so everything to the left, most of them, everything that's green, blue or yellow on this chart, or orange and green, and everything to this steps right here. These are all metals, all non-metals. Everything to the right are non-metals. Non-metals, metals. Okay, so non-metals, where my hand is, metals.
Are these metals?
Those are called transition metals. They're kind of act like metals sometimes, they kind of don't act like metals sometimes.
To the metal.
They're metalloids, exactly. Okay, so what we do is we take the metal, now in your book it says this way, we take the cation, the one that's going to take on a positive charge and get rid of an electron. It's also the metal. I think it's easier to remember it that way. You're going to name it first. Its name goes first. All right, the next atom that's getting the electron, the anion, is going to have its name second and an IDE on the end of it. Sodium, that's a metal. Chloride. It's not sodium chlorine. When chlorine takes on a charge and becomes an ion, it changes its name to chloride. Okay? That's just a traditional way we do it. What is sodium chloride? So sodium chloride is salt, right? And notice, what does that mean? I have an Na for sodium, a Cl for chlorine, and when I have them together, there's that little line in between them, and that line is called a chemical bond. It's a bond. They are bonded together. Okay, and they're bonded together because they have different charges that attract each other like a magnet. Yes.
I thought that line in the middle showed that they were sharing electrons.
No,
Oh.
it's a bond. Some of them are,
That's what the band.
not in ionic, only in covalent. Okay, they are not sharing electrons. Ionic, Molecules do not share electrons. Ionic molecules give and take electrons.
Then
Okay.
they're just like bonded like that.
Yeah, but the line shows that they're bonded together. In fact, I can show you. I've brought this many times. I use it for chemistry today. The sweater. Trouble. So if I have a chlorine and I have a sodium, okay, what'll happen is the sodium has this little, just this one little electron sticking out on the side. Look how many electrons chlorine has. 1, 2, 3, 4, 5, 6, 7. Just needs one more. So sodium will just say, here you go. But now since it gave it to it, since it gave it over to it like this, now they have a charge associated with them, so they stick together. So this bond is called an ionic bond. It's not very strong. You see how it fell off, right? So it's not very strong. But we'll see some stronger bonds here in just a second. All right. So what happens is sodium's got that little electron out there in that outer shell called the valence shell, right? The valence shell. It's going to give it to, here's chlorine with 7. It just wants it right there. But when that happens, sodium takes on a plus charge because it has more protons, and then the chlorine takes on the negative charge. So we have our cation and our anion, and now they're kind of stuck together. All right, so we see what is it called? It's called sodium chloride. Sodium chloride. That's how we're going to name these guys. So let me tell you that naming ionic compounds is easy and fun. Naming covalent compounds, yikes. Even my chemistry kids were like, ugh. Yeah, so a lot of our covalent compounds just have, like for instance, we have something called water. We just call it water, right? But it really should be called dihydrogen oxide. 2 hydrogens and an oxygen. Okay. All right. So here we go. Here are some common anions. Anions. These are the ones that come. Their name is second in the group. Okay. So the anion of hydrogen, when it loses its electron, it's going to be called hydride. I'm sorry, it gains an electron. It's going to be called hydride. Fluorine's going to be called fluoride. Chlorine, chloride. Bromine, bromide. Iodine, iodide. Does that say iodine? It should say iodide. 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 Oxygen, oxide. Sulfur, sulfide. Nitrogen, nitride. Phosphorus, phosphide.
Why are
Okay?
they all ions?
Because we added that IDE on the end of it to show that it's an ion. That is the way it's done. Why they did it, I don't know for sure. And on this one right here that says iodine right there, there may be some disagreement among scientists, but I definitely know that it's called iodide, unless something has changed. I don't know if that's a typo. I don't know if that's a typo. Not sure. Okay, but those are some common ones. All right, and so now let's name some. Okay, for instance, if I have sodium, my cation is, so these are all metals, by the way. Look, sodium, potassium, lithium, magnesium, calcium. Each one of those would be on the left side of that stair step on your periodic chart of the elements, making it a metal. Okay, and these are the anions or the nonmetals. Bromine, chlorine, sulfur, oxygen, and iodine. So, if I put sodium and bromine together, what do I get? Sodium,
Bromide.
bromide. Now, what if I put potassium and chlorine together? I get what?
Potassium chloride.
Potassium chloride. Fill it in your blank. If I have lithium and sulfur, what do I get?
Lithium sulfide.
Lithium sulfide. If I have magnesium and oxygen, what do I get?
Magnesium oxide.
Magnesium oxide. And this will tell us on our iodine on here. If I have calcium and iodine, I get
Calcium iodide.
iodide. Of course, I wrote that, so
These are different ones.
I just don't know why they didn't put it on the other chart. Okay?
Oh,
So you see, you will probably have in your test and on a quiz, I'll ask you to name some of these things. So the very first thing you have to figure out is it ionic? And you'll have to say, oh wait, is it a metal and a nonmetal? If it is, it's ionic. But if it's like a bunch of carbons and oxygens, that's not going to be ionic. You know. By the way, don't count hydrogen as a metal. Hydrogen's not a metal. It's special. It's in a special place. I know that it's over on the side of the metals, but it's special. Yes.
On the test, there was one asking which ones are like iron compounds. I think, and
Which one's
I
what?
got it wrong because I wasn't sure the symbol was a metal or not. 'Cause I love to look at the.
Yeah, you can always use your chart of elements. Yeah, that's something you can use. And if we need that for a quiz, then I will provide you with my chart to look at. Had I known we were doing this much chemistry in this new edition of this book, I probably would have purchased you your own chart like that. I give it to my chemistry kids every year. I didn't think you were going to need that much. I'm really surprised, honestly. All right, let's talk about some unusual cations, ones that are going to get rid of their electron and take on a positive charge. Right, cats are positive. Yay for cats. All right, so sometimes some of these strange ones, notice on your chart, look at your chart, notice where copper, Cu by the way, copper and iron, Fe by the way, lead, Pb, I know what that is. Anybody see lead? Oh yeah, it's over here to the right a little bit. Number, I don't know if this is the numbers on it. Number 82. And chromium, but notice some of those are right there in that, remember I told you the middle group tends to act strangely? All right, so these are in that group of kind of weirdos, all right? But they're somewhat predictable, but not 100% of the time. So in other words, when I tell you about using these metals, I'll have to give you additional information for you to understand how to use them. Sometimes copper wants to gain, lose one electron. Lose one, so having a 1 positive, 1 plus on there, right? It actually looks a little bit like that in a powdered form. Did that surprise you a little bit that copper would be that greenish color? Okay, that's called copper 1. And the 1 is in parentheses in a Roman numeral. It's a Roman numeral 1. But sometimes copper wants to get rid of 2 electrons, and so it takes on a 2 plus ionic state. And it looks like this, by the way. Beautiful. Copper's very blue. But we call that copper 2. Copper 2. Roman numeral 2. All right, so if I have this in ionic, if I give it to you, in fact, if you see something, name this one and it says Cu with a Roman numeral 1, and you already know we're talking about ionic compound. Okay, kind of a giveaway there. All right, but iron does it too. Sometimes it takes on a 2 plus, sometimes it takes on a 3 plus. So sometimes it gets rid of 2 electrons, sometimes it gets rid of 3 electrons. We call that iron 2 and iron 3. Lead 2, lead 4. Okay, and then chromium 2, chromium 3. Those are just the kind of unusual cations that are out there. Yes?
How many valence electrons does it have?
You have to look on the chart. Where are they? Which one are you talking about? Chromium?
In the yellow section.
Chromium, what number is it? It's Cr.
Oh,
It's number 24. Okay. So we're going to see here that it's in group, well, we can call that 6 right there. 1, 2, 3, 4, 5, 6. And so it's going to tell us that here it's going to have, yeah, see, it's in the group of weirdos. Trying to draw it would be unusual. Okay, let me see if this tells me. Yeah, so it's something we'd have to look up, and that's the point. That's my point. My point is, I have to tell you how many electrons it's giving away. I have to. Otherwise, you're not going to know. All right? If you were doing copper, you would say, well, this one's blue, so it's obviously copper 2. You'd see it. That kind of thing. All right? So if you end up with a question that has a Roman numeral, remember that Roman numeral is telling you how many electrons they're going to get rid of. Okay? All right. Okay, now, to complicate things even more, if they're not complicated enough already, there are these things called polyatomic ions. Okay, so a polyatomic ion is a group of atoms, don't worry about this word for now, this covalent group, but a group of atoms that has a positive negative charge as the whole unit. The whole thing takes on a charge. They stay together. They stay together and the whole thing has a charge. Polyatomic ion. Within the actual grouping, it looks like here it says it's covalently bonded. They're bonded together there, but they stay together. This is important because if you're doing a chemical reaction and you want to know where everything's moving to, that group has to stay together. It's like they're glued together. They have to stay together. Their chemistry is different because that group stays together. So here are some common ones. You may have heard of them. Ammonium. You've probably heard of ammonium. No ammonia?
I've heard of it.
Yeah. So it's NH4, and is that, oh gosh, we can't see that number, that little, is that a plus sign?
Mm-hmm.
Yeah, is it a plus sign? Yeah, it's the only plus sign one on there. So ammonium's the only one. There was actually a song I almost put in here, this girl playing her guitar for all these, but I couldn't do it. I have difficulty doing songs in science. They're really corny, you know. And maybe you could learn it and sing it, you might know it, but I don't know. It's the only positively charged one, though. Then we have hydroxide, which is an important one, OH negative. I'll let you know that anytime you see an OH like that, you're going to know we're working with a type of a chemical called a base, which is the opposite of an acid and base. We have nitrite, NO2 with a -1, sulfite, SO3 with a -2, chlorite, ClO2 with a -1, hypochlorite, ClO with a -1, carbonate, CO3 with a -2, peroxide, O2 with a -2, nitrate, NO3. Look here, we had nitrite and nitrate. The endings mean something there. NO3 with a -1, sulfate, SO4 with a -2, chlorate, ClO3 with a -1, and phosphate, PO4 3-.
So if it has an A, then it has one
There's a
more.
method to the madness for sure. So yeah, sulfite versus sulfate is 3 versus 4. Do we have another 3 versus 4?
Yeah, but 2 versus 3.
2 versus 3. 8, yeah. Okay, so it has to do with which one's more, I guess. All right, y'all wrote down your blanks. You filled in your blanks. Group of atoms that has a positive or negative charge and act as a unit. I'll pull one up here. So this one is carbonate. This is carbonate, which is seen right here. So CO3 with a -2. Here's the C, here's the O's. There's our -2. Notice it has a bracket around it, and that -2 shows you that that -2 confers to the entire molecule inside there. The whole thing takes on a -2. And the whole thing stays together. It has to stay together.
What if you write it and took away the charge? It would be imbalance?
You can't. But we're fixing to do something very similar to that. In other words, when we put it into a formula, a chemical formula, you do move that. That's what we're learning today. It's not very fun. Okay. Here we have something, look, we have a SO4 with -2. So the way this should be written is our parentheses and then our 2- here. And then we wouldn't have to put those negative signs right there. Okay? But that's showing that the SO4 is an entire, and that's sulfate. Is it sulfate? Let's go back. SO4, -2? Yeah, sulfate. That's the name of that polyatomic ion. The whole thing will travel together when it's going in there. Now we're getting to the meat of the lesson today. Let's take a small break to get our lab set up, okay? So I'm going to we have 2 beakers here. This group here and that group over there. We're going to be working together. This takes sometimes a little time to set up. So we have water in this beaker. I'll pause this for a second. Y'all remind me to start